Problem 6. What is the slope of the line tangent to the curve y equals arcsine of 3x at the point at which x equals 1/9? All right, as soon as I see the word slope of the line, I know that it's asking me to find a derivative, so that's what I'm going to be doing. And so to get this is an arcsine problem, and if you recall, the derivative of arcsine of u is du over the square root of 1 minus u squared. So that's the formula that I'm going to be using. So y prime will equal du, since this would be u, would be 3 over the square root of 1 minus 9x squared, because remember you have to square the 3 and the x, so that's what I get for my derivative. And then from here, it does tell me that my x value is 1/9, so I'm trying to find the slope at x equals 1/9, so I'm going to have 3 over the square root of 1 minus 9 times 1/9 squared, and this will just take some simplifying on my part now, so square root of 1 minus 9 times 1/9 squared would be 1 over 81, okay, and then I'll get 3 over the square root of 1 minus 9 over 81 would reduce to 1/9, and I know that this is an improper fraction, so there is something that I need to do with this. 1 minus 1/9 will give me 8/9, so I'm going to have 3 over the square root of 8/9. And then from here, I actually am going to just keep simplifying. The square root of 8/9 is the same thing as the square root of 8 over the square root of 9, and the square root of 9 is 3, so this will be 3 over the square root of 8 over 3. And now we can cross multiply. I'm going to make the top number 3 over 1, and then if I multiply it by the reciprocal, I'll get 3 over the square root of 8, so I'll end up getting 9 over the square root of 8, and I could stop. We could go a little bit farther with multiplying by the conjugate and simplifying the radical, but that's as far as we really need to go. All right, number 7, if f of x equals e to the ln x squared minus 8, then f prime of 3 is equal to what? All right, there are a couple different ways to work this problem. If you notice that the e and the ln cancel each other out, we could actually simplify this problem into x squared minus 8, and then it asks me to find the derivative at 3. So f prime would equal 2x, and so then when I find it at 3, it will equal 2 times 3, which is 6. Okay, so let's say you did not notice that. I would just like to show what we could do. The derivative of e to the u is e to the u du, so if we just let this be u, my e to the u would just be e to the ln x squared minus 8, and then we'd have times du, the derivative of ln x squared minus 8 would be 2x over x squared minus 8, and then we could plug in 3, and when I do that I'll get e to the ln of 1 times 2 times 3 over 3 squared is 9 minus 8 is 1. So the natural log of 1 is 0, so I'd get e to the 0, which is 1, times 2 times 3, which is 6, which I again get 6. So if you did not see that, you could still work out the problem and get the right answer. All right, number 8. The rate of change of the area A of a figure with respect to time t is directly proportional to the cube root of the area. Which of the following is a differential equation that describes this relationship? First of all, it says which of the following is a differential equation. The equation has to have a derivative in it, so I can automatically cross off A and I can cross off B because they do not have derivatives in them. Right? The next thing, it says the rate of change of the area, so I know that's going to be dA dt, which they both have, and it's going to equal, and it says it's proportional to the cube root of the area. Well, the cube root of the area would be the cube root of the area, right? And if it's proportional, there always is a proportionality constant. Even if you didn't know that, notice that it says the cube root of the area. That's how I would know that I had to pick option D. All right, number 9. The function f has the property that f of x, f prime of x, and f double prime of x are positive for all real values of x. Draw a possible graph. Well, let's just look at what that looks like. Okay, if f of x is positive, that means the graph will always be above the y-axis, because I'll always get positive answers for my y. Okay, if f prime is always positive, that means my graph is always increasing. It's never going to decrease. Okay, and if f double prime is always positive, that means that my graph is concave up forever and ever. Okay, so although we have many samples that we could do for this one, okay, the graph always has to be above the x-axis, it's always increasing, and it's always concave up. So the one that I thought of when I did this was just an exponential graph, because notice this graph is always above the x-axis, it's increasing, and it's concave up. Right, number 10, draw a graph that has the following characteristics. At x equals 2, the graph is discontinuous. At x equals 3, the graph is continuous and differentiable. And at x equals 5, the graph is continuous but not differentiable. Okay, if the graph is discontinuous, that means there must be a hole or an asymptote. If the graph is continuous and differentiable, that means it connects very nicely, there are no sharp turns. Okay, at x equals 5, if it's continuous, it's nicely connected, but if it's not differentiable, that means there must be a sharp turn there. So two different possibilities that we could have for this graph. The first thing that we could do at x equals 2, if it's discontinuous, it could have an asymptote there. And then at 3, it's just going to be a nice smooth curve. And then at x equals 5, we have to have a sharp turn going on. So I'm just going to put some points here. Let's put a point there and a point there. So we've got a nice curve going on until I get to here, and then there has to be a sharp turn. So that would be one thing that might happen. Another thing that we could have happening, if it's discontinuous, it could just have a hole at x equals 2. So if I just put a hole at x equals 2, and then at x equals 3, it's just a nice smooth curve, and then at 5, it has to have a sharp turn. So I could have something that looks like this, something like that. So those are just a couple different examples you could have. I'm sure there's many others that might work.